Thank you, everybody, for having us to come and share some time with you guys. It's just amazing. University of Illinois is and railroad engineering is just way out in front of the curve for all the departments. You guys are doing amazing stuff, and you're working on the right things that are adding value to us in the railroad engineering. We're going to share a few things we're doing. We got a lot of stuff that's going on, but we try to get down to a few things we're working on, and then we can, if you have some questions, whatever, we can answer those later. So the things we're going to talk about, a couple things we're going to talk about a little bit about the rail industry health. I think that's important for people that are thinking about maybe a railroad type careers, kind of understand where we're at, where we might be going. Also talk about, look at the profile and a little bit of an infrastructure of UP. Then I'm going to try to talk about some of the track assessment technologies that we're using at UP, talk about some of the vision-based systems, and then talk about the rail generation steels that we're looking at. Also talk about, and then Steve's going to talk about the high-speed passenger turnouts. Then he's also going to talk about concrete and some of the concrete advanced fastening systems. You guys have been integral as part of some of those. So let's talk a little bit about the railroad industry. And, it's kind of interesting where you kind of look where we were in 1940 compared to where we're at now, or all the way back to 1916 even. Looking at the route miles that we had, there was about 254,000 route miles on there. Since 1940, if you compare that time to 2011, we've had about 93% reduction in the miles out there of railroads. We got, railroads have kind of condensed, and we've got less miles, and so we've gotten smaller as far as the route miles are concerned out there. But now we look at tonnage. From 1940 to 2011, there's been a 460% increase in ton miles. Ton miles are, carrying 1 ton of freight a mile. So 460% increase. So what that's doing is demanding us to do different things, be able to handle different types of loadings and things that we had to do earlier in earlier lives. Excuse me. If you look at the average tons per car, which is another thing I always like to look at, there's a 230% increase in tons per mile. Tons per car. So that is a huge increase. So that's all affecting us. When we run a car track, that's more tonnage, more tracks. And we have places out there where our heavy axle load area, we're up at maybe 135, 136 cars per train out there. 20,000 tons. So UP, a couple questions, little things about that. We're largest railroad in North America. We operate in the western 2/3 of the United States. So we get the challenge of oceans, we get the challenge of deserts, we get the challenge of mountains, we get the challenge of a little bit of everything going on. We've got islands. So we get a great opportunity to try to manage the geographical area. UP is a Fortune 143 company. We had revenues of $19.5 billion, and we really see ourselves sitting in a really good place to be able to grow, and a lot of the areas we serve are places where the growth is. We've got, in the department-wise, we've got about 45,000 employees that are all part of the Union Pacific Railroad. Headquarters are in Omaha, Nebraska. We have our dispatching centers in Nebraska. A couple other things we have some of the, UP has some of the heaviest things that we're trying to do, going through Nebraska, up through Nebraska, Wyoming, Nebraska, down Kansas, some of the different areas. So we're running a lot of freight trains down through here. Okay, we have about 32,000 route miles of trackage. Route miles is like you might have 2 tracks out there, but that's how far the total route miles are. We got about 112 million ties out there, and we got 31,000 turnouts. A turnout is where you go from one track to another. So, I mean, it's a lot of stuff that we have to maintain. A lot of tunnels. We got 62 miles of tunnels that we maintain. And we have a lot of facilities that we have to do. And it takes a lot of money and everything to try and maintain all these facilities. Commodities we do, we got about 2 million carloads that we do a year of energy, which is your coal. We also get into the industrials. We're handling like might be lumber, like fit into your industrial. Agricultural, we're about 0.8 million cars that we do a year. Chemicals, we're about 0.9 million. We're one of the largest handlers of chemicals. Also, intermodal is about 3.6 million cars of the intermodal, and that's a really growing area for us. Well, we're really growing busy on all the intermodal. So it's kind of interesting as that growth goes. Also, we're also a bit on some of the energy right now, but we're having some big increases to offset it in some of the other areas of the business. Okay, tell you a little bit about our engineering department. We have a design group. We have a track renewal group. They're the guys who go out and do all the big gangs out there. They're going out doing new projects, new rail ties. But that's kind of what the track renewal group does. The construction group are the guys that are going out there building it and everything up to the track, and then the track renewal group takes above that to start building on top of that. Also, we have the structures group. They've got all the structural responsibilities, and then we have a signal group that does all these signals. The signals are what control. Like it goes up. You go up to are all about. Yeah, our department at UP, we actually have 12,500 employees that are engineering employees. So we're a big engineering firm, basically, is one of the ways we kind of look at this. We got about over 5,000 vehicles that we do, and when you look at equipment, a lot of equipment to do the work is we're almost about 4,500 pieces of equipment out there that we do work with. So you have a lot of things that you have to maintain here also. So I'm going to kind of talk about one of the first technologies that we do, and I kind of look at these as being remote track assessment technologies. Talking about VTI, and Union Pacific is one of the first freight railroads to implement this, and we've been doing this since about 2000. What VTI is a technology that we can measure the Okay, how's that? Is that better? Okay, so and also so the things we're kind of measuring is car body verticals, we call them. We do car body laterals, we do truck laterals, we do axle verticals, which are high impacts on the rail, and also we do what we call mid-chord offsets, and also we do combo clusters. Now, why is this important? Well, it's kind of neat stuff because for us, for 7 business, we don't have people on the track. We have 350 track inspectors that go out and patrol our tracks. But with these VTI systems, we have 2 locomotives and 2 cars. We're able to go out there and run 24/7 and look for problems with the track. Now, if we get a problem, we have a high hit. The guys set up where they can set cell phones on their cell phone, they got a high hit. Now, if it's a high hit, they got to do something within about, we do something with 24 hours. 7 days in order to handle that. And the way we handle Uh, yeah, a couple other things we've done. There's, and it's one of those things that when you go out and look at these things, it's hard to see. But underneath technology that we've done is one thing, and this is the thing that's finding profile spots for us. Another thing that we're finding out there was these were things that we weren't seeing with our evaluation car. We go across the got our evaluation car smarter now, so we can find short column. And they're finding profile slides coming into your jobs. They're finding broken up concrete ties, for example. We're able to find this with this technology. I'll talk about a little bit later. There is one of the technologies that we got the idea that we need to have something on there. Here's another example of the using this. Where you get track transitions in the railroads is a big maintenance. You'll get a transition change it from your track modules. It could be up to 10,000 psi. And this is finding. Another technology which is on this new exception for us is called a combo cluster. Now, what a combo cluster is, it doesn't meet any of the other levels, okay? And it's kind of interesting, but when we kind of went back behind there and we kind of learned a little bit, we found places where we had derailments where we weren't finding things out there. Some of the technologies. So combo clusters were they're saying, hey, you got a problem. We're finding some interesting things out there. But it gives us an idea of things that we need to do. So we have a high level and a medium level and how we go out and handle those. Some of the things we're finding, non-supported joints. We found like an IJ. We have a stripped IJ that pulls apart. We got broken ties. Sometimes we're finding, we'll find the broken ties on this. And track transition issues, going from the wood to concrete. You'll sometimes see those with that. So this is some pretty good stuff that's been a very good tool for us. You talk a little bit about the autonomous track geometry system that we are using, and this is still the FRA has one actually running out there. We've had one on a truck for a while that we've been actually running the system out there. But what this does is actually give you track geometry measurements, which you can be an FRA or it could be a UP exception, for example. And we're on this thing until we people out. If we're gonna get guys in the middle of the night go out and look at something, it's got to be something. To that point in the technology probably will implement. Another thing that we haven't talked about earlier, this is a tool that's actually developed, was actually out. This is actually called MRail, and it kind of looks at the vertical deflection. And what happens is that we look for changes in the vertical supports. So we can find places where you might find a place where the broken ties were. We were finding the short cord stuff with this technology that we weren't seeing with our evaluation cars. We also put this onto the VTI stuff with the technology we use for this, so we were able to find things. So we're able to move that technology over there to find the problems for us that were short cord related. So right now we have a test. We're running it every month, looking on our South Morrill sub, which is our heavy axle, heavy tonnage subdivision. And we're doing it every month. We're going to look at degradation rates for that to see if we can learn anything from that. Next thing to talk about is machine vision. Machine vision is a technology, and you guys have done a lot of stuff with machine vision up here at University of Illinois. And this is where it's kind of the next step function improvement that I see for the industry. And the things that this can do is basically are vision-based systems that can be used to look at our assets out there, trying to understand and do inspection, trying to understand what's out there, so we can get a good health or understanding of the health of the railroad. Some of the opportunities that we have out there are the concrete tie evaluation, the wood tie evaluation, rail surface conditions. You can look at joint bar inspections. You can do brands inspections, fastening recognition evaluation, rail seat abrasion, and on concretes. And so what I think long term here, you might want to be reducing the offset what the guys are out there inspecting. Maybe reduce something from a maintenance task. And then also, obviously, understanding all of our assets out there is a huge benefit for us. Next thing I'm going to talk about a little bit is we're going to kind of go into the rail side of this. We're basically using 100% head hardened rail right now. 72% of our head hardened rail is a 400 plus Burnell. Look about 410, 415, and drive in that area. And then we're doing about 28% we're doing with the 360, the 370 Burnell. And there are some of the domestic or manufacturers went out and they came up with some technology that came what we call an intermediate strength. We were doing standard strength, and we had standard strength steel that we're using. The other thing that we're doing here, this is going to be the first. Probably the first in the world here, but we're going to have 480 foot long rail. What happens is we buy a lot of our premium strength rail from Japan, and rail out there. Also, the life of the rail. And I'll show you why we need to do point welds. Here's a picture of a plant weld here. Basically, induction coils that they're developing, so they'll be able to perform post-weld testing, are the plant welds. And basically, the objectives of all this is trying to reduce the residual stresses and with it the heat affected zone. This is a big issue for us because anytime you don't control your heat affected zone out there, then that can cause problems with your welding processes. Even with our hand or our field welds, we call it the process that we do in the field without control and stuff. That is something that would help that also probably. But this is something that is a big issue for us for the industry that we're working on here. We have there's two what they call mega sites in the U.S. There's heavy axle load mega sites we call them. one on the eastern, on the Norfolk Southern, with the eastern mega state. We've got the western mega state on this heavy axle in the South Morrill subdivision I was talking about earlier. We do a lot of testing up there. I mean, they always take things out there. They'll try and break things out there to teach the site facility. You guys got things you're trying to break in here too, and if they pass those levels, they ship them out, and we'll test them out there because we can break them out there with the tonnage that we get. So it's nice to get that stuff out there and get it tested. Then we can get there, and if it survives out there, it's going to survive in the environment. But some of the we kind of come up with results that rolling contact fatigue can be a really significant issue if it's not controlled. Right. Really big benefits from doing some things such as easy as putting preventive grinding or doing some top of rail friction control to control the RCF and also reduce some of the wear out there. And our premium steels are showing excellent wear performance. Big problem still for us is the welds. We've got to get the welds better so they match up with the rail, but that's a really good way for us to go here. Also, here's a couple of charts. The friction control is effective controlling RCF and reducing the natural wear. And we've got about 960 tons of rail up there without recurring RCF on there, which is a lot. Preventive grinding is effective, but we need more rail section. If you're out there doing grinding, every time you grind the rail, you got to take so many thousands of rail off. And so if we can get ways to not do that, that gives us life of the rail. And some of these areas, maybe you're going through. You could be going through 3 times a year, maybe doing your grinding based on your tonnage that's running up there. See rail wear on our 2-degree curves. Test curves, we've got about almost 1.7 mgt of tonnage on that. And with that, we've seen 17% of the railhead section on the rail with grinding. 12% of the railhead on the test curve was with friction control. So you had less wear with the friction control actually than doing the grinding on it, which you would think. The premium rail. And then, in revenue service, we replaced the rail in about 2013 because we started getting some sporadic rolling contact fatigue. And what we've done on there is a couple things we've done on this thing is really we've seen some really good benefits on the lower curves. And one of the reasons I wanted to study some of the curves out here is to really look at the 1 and 2 degree curves, really to understand what we need to do, because we do a lot of things for maybe 4 degree curves and up, but trying to really understand the 1 to 2 degrees, huge benefit for us if we do the right things and do the right maintenance things there. So, to continue to understand is really good. So the type of things we're going to continue to do, I think, is really to monitor the performance out there on the premium steels. Also, we're going to continue to develop and give our next generation of the that have better RCF, resistant, wear resistant, and internal flaws. That's all the thing we're always trying to do with getting improved steels. And we're going to develop and demonstrate optimized strategies to prevent RCF, and then we're going to reduce the rail wear on this. So next thing I'm gonna have Steve come up. Steve is just got promoted to the director for this job, and this is a big job in Union Pacific. And he's going to do a great job for Union Pacific, and he's going to take everything to the next level. He's done a really good contribution where he's already been at, and we're looking at great things for him.
Pressure's on me now, I guess, huh? So I did catch a little flack for not having the guts to wear my University of Nebraska shirt today. I thought about it. It was in my suitcase, but. This is the group that I'm now in charge of. Many of you know my former boss, Eric Geringer, who's now moved on, is working with UP as a director of track maintenance in the Minnesota area. But my group really handles a lot of everything from the rail down. We handle ties, turnouts, ballast, surfacing, and then we also operate the geometry cars, looking for surface defects. So really have a broad range of different items within the engineering group that we're responsible for. The two topics I'm going to talk to you about today. The first one is, both these are very near and dear to my heart, but the first one is one that's very close to this area too, which is a mixed-use passenger freight turnout design. There's a lot of work in the area, obviously, on this St. Louis to Chicago corridor, and just wanted to talk a little bit about what UP's been involved in getting some of this 110 mile per hour track to work. Starting out turnout facts, Dwight kind of showed there some highlights, but we have over 13,000 mainline turnouts, and that's just mainline. There's over about 20,000 or so yard and industry turnouts as well. There are a whole bunch of different sizes. You know, UP is a collection of former railroads. Every former railroad liked their own turnout size, so everything from 7s to 30s are out there somewhere on our track. Passenger service on UP is kind of a unique piece for us. It's not our core business by any stretch of the means, but it's not foreign to us either. You know, we run over 700,000 or have over 700,000 weekly riders from passenger standpoint, over 1,700 trains. A lot of different corridors throughout the western U.S. But this is a really unique animal for us, this Spissel line that we refer to it as, which is the St. Louis to Chicago Amtrak corridor. It's essentially our Springfield and Joliet subdivisions through Springfield, Bloomington, into Chicago. And it's going to be an Amtrak key connection point, 110 mile per hour class 6 track. A lot of it's already been upgraded, but it's going to continue to be upgraded. Concrete ties, 141-pound rail, and a lot of single main line that will eventually become double main line. So here's a photo, kind of a before and after look at what's going on out there, going from, again, the wood ties to the premium concrete and 141-pound rail. So it's a unique operating environment for UP. We're traditionally classes 1 through 5, freight railroad, and it's got some interesting operating requirements. 110 mile per hour, you really have to have key interchange points for train switch from one track to the next, keep that network fluid. And you know, we really wanted to find turnouts that head to higher speed, the 50 mile per hour or greater for this route to really keep times down. It's got to be competitive with alternatives out there, vehicle traffic, airplanes, to make it work. A lot of the traditional turnout designs, they're designed to maximize space, not so much other key characteristics. You can go longer turnouts, but they increase costs and maintenance. So a lot of the drive between our current turnout designs is low space, low footprint, low maintenance. Lateral forces are really the key driver in all this. As you switch from one track to the next, you experience a ton of lateral force. We've done a lot of strain gauging work on the UP trying to quantify this lateral force. And when you reduce lateral forces, it's two big things. You reduce, especially for passenger trains, what's felt by the passenger as they move from one track to the next. You also reduce maintenance. You reduce the amount of loading in the turnout, you're going to reduce maintenance. So here's a sample of one of our number 20 turnouts in a key freight corridor. And you can see there's really a high peak load. As soon as you enter in the switch, about 6 feet back, 6 to 8 feet back from the switch point, there's a really high peak load. If you're a passenger in a passenger train, you're going to really feel that. What we're really looking for is more of a smooth force transition. As you move from one track to the next, we really don't want you to be able to feel it. We want to reduce that lateral loading, get a much more consistent spread through the turnout. We approached one of the big turnout vendors in the U.S., Volks Alpine Nortrack, to really kind of see what we could do for this specific corridor. And what they really suggested that there's a type of switch called a semi-tangential switch. They're been used heavily in Europe. They're starting to migrate to the U.S. now, but Metrolink in California had used some of them. And what tangential essentially means is that the entry angle at the point is very low. So you can see that it's a very long, very thin switch point. So the key is you want to really gradually, very slowly move the force as you switch into the turnout track from the mainline rail to the switch point. You can see there, the top curve is kind of a traditional type curve. Your tangent, boom, you're right into the curve. The bottom one is a spiraled curve type design. So you're really trying to gradually enter into that curve. On the railroad, that's what we normally use in most of our curves is a spiral. You slowly ramp into the curve. It's not just bang into the curve. So we're really trying to adopt that for these turnouts as well. So you can see some differences between the existing 24 and the semi-tangential design. The big one is that entry jerk. Jerk rate, you know, Amtrak guys know this. It's you know, how much force is felt by the passenger as they make this transition. So if we want to keep that entry jerk below 0.1 G per second, we're really looking at a 60-mile-an-hour turnout by using this revised design. You can see here some of the differences in the turnout. Our standard turnout, it's about 30 feet longer. It's much longer, much thinner switch point. You can see here some sample photos. The one on the left is the standard design. The one on the right is the semi-tangential. So it's much longer switch, much longer, thinner switch point. There's another photo of one in Athol, Illinois. Went in a couple years ago. So moving forward, we've had a tremendous amount of success with this turnout design. We're really trying to adopt it now in other aspects of our business, especially the freight corridors, the heavy tonnage corridors, where we can use some of this geometry too to reduce impact loads, reduce maintenance interventions on switches. Using some other key features to help strengthen in addition to this. We're going to keep monitoring these turnouts. We're going to do some additional strain gauging just to see how they're performing, if they're meeting our expectations. And then, this is the spilled coffee test. As you hit that turnout, how likely is it for a passenger to spill their coffee as they go through there? The second piece I'm going to talk about is concrete tie and fastening system research, and it's very interesting. The last few days we've been talking with a lot of individuals here at U of I, and you guys are engaging in a lot of the same stuff we are. Really trying to get a better concrete tie, a better fastening system. It's been very interesting, very eye-opening for me. For concrete ties, we began utilizing heavily in spot applications in the 80s, really more heavily in the 90s. We have over 3,000 miles that are concrete, specific applications, high curvature, high tonnage, especially in Nebraska, Kansas, coal routes, Iowa, and locations where operating conditions dictate. And we've utilized 9 different fastening systems over the years in various different quantities. The key thing that we have to always consider, being the business that we are, is what the economic competitors are to concrete ties. It's very easy to design a $400 concrete tie that's going to last for forever, but the economics will never work. So we always have to be mindful that it's got to be competitive with wood, it's got to be competitive with steel, and competitive with composite. So it's something that we always have to keep right at the forefront. Make sure our shareholders are happy. So what's driving our research right now? For us, it's the highest maintenance areas. The tangents aren't so much an issue. It's really curvature and turnouts is where we have our problems. And we've done an absolutely tremendous amount of work with VA and Nortrack in the last 3 years to work on turnout ties and turnout designs. Really, curves are what's the big animal that's left for us to work on. Really trying to increase the life cycles, make it last the life of the rail. Really trying to minimize the amount of maintenance interventions, increase the durability. And on the horizon is also the increased axle loadings. If we go from 286 up, being able to handle it. So concrete ties and curves provide increased lateral stability. That's one of the big features of them. They really prevent us from seeing a lot of movement in the curves, and increased gauge restraint. There's a lot of forces in action in curves that you don't have in regular tangent track. And we talked a lot about that here the last few days. You have thermal forces. You have the dynamics of trying to push up on a curve or push down on a curve. So there's a lot more force going on in these curves as there is to the tangent that we have never probably done a good enough job considering with designs, and we're really trying to do a better job going forward. So you can see that lateral force really impacts the whole system. It puts additional wear on that insulator, puts additional wear on the clips, additional wear on the rail. So it's something that we're trying to be very mindful of going forward. So these forces cause a lot of issues on the concrete ties. Insulator wear, pad wear, huge problems for us that we're trying to address better going forward. And they drive a lot of the other critical issues: rail seat deterioration, shoulder wear, leg screw wear, wide gauge, excess can, all this other stuff that comes along when that fastening system begins to wear out prematurely. So here's some sample photos of what we see out there. The insulator wears out, breaks down. Eventually the rail starts to eat into the shoulder. Next thing you know, you have all the other issues that go along with that: wide gauge, cant, all those other problems that we want to avoid from the word go. How do we try to figure out where these problems are? For UP, we're very aggressive, and that's the key point I want to leave here today. Although those pictures are ugly, we're very aggressive in looking for that and eliminating those when we see them. We have the human inspectors. We measure a lot of this stuff by hand to evaluate tie performance. Geometry cars out there running all the time looking for the key factors such as base gauge and rail cant that they can look for to find problems. We have gauge restraint measurement systems, and then we have tie raters too that go out and evaluate these conditions. So here's a sample EC car strip chart. You can see there's a lot of different things they're looking for, but the big ones are base gauge and cant. We can pick up problems in the curves that tell us, okay, we need to go back out and take a look at this one. And we use these very heavily to help us evaluate where we need to go in and replace ties and do other maintenance interventions such as replace insulators. So again, curve failures are really what's driving our internal research now. We're looking for ways to extend the fastening system, try to get it to match the tangents, match the life of the rail. We're by no means there now, and we may never get there, but we're going to push towards that. We got to have something that our production equipments, our people can maintain. We can't just put something out there that's out there, and when we have an issue, we can't attack it. And then something that can be done on a large scale, that we can put enough of them in to attack the problem. And something that can be inspected visually is key too. So we're going to do a pretty big project here in 2013. We're going to put in over 6,000 ties of 8 different designs and various curves up in Oregon, between 3 and 12 degrees. Really trying to quantify what's the best existing system or new system for handling these loadings in curves. Which one's going to provide us the best life? We're going to evaluate them every aspect from fastening system degradation, rail seat abrasion, center binding, looking for all sorts of an overall system performance. And then we're also going to do some cycle testing of these same tie designs with our MTS machine. So again, we're also looking at some other key concepts that are out there right now, using stirrups inside the tie, provide internal end containment, trying different tie designs, different section designs to give us a tie that has the best strength. Looking for full face insulators. Obviously the key for an insulator is if you give yourself more bearing surface, there's more wear surface. It's going to hopefully take longer to wear. So looking at systems that use the whole width of the tie or even extended widths to give us a bigger bearing surface. And then looking at different pad and rail seat epoxy types to try to see what's the best one for preventing rail seat abrasion and rail seat deterioration. We have an MTS machine. We're getting it up and running. It's very similar to some of the stuff that's going on here at U of I. We're very proud of it, but it's been quite the beast to tackle. But it's capable of mimicking track loads. It can do up to 50,000 pounds, rate of 5 hertz. So we can do about 3 million cycles, which for us is about roughly a year in track in about 2 weeks with this machine. So that's really where we have a lot of issues with the existing standards and testing requirements. They call out 3 million cycles. For us in some of our heavy tonnage lines, that's a year. So we're really trying to push that forward too and look to push it out to 9 million or 12 million or 15 million cycles to really give us a better representation. Epoxy coating is something UP's been very heavily involved in. We've had a lot of success with it. We coat the rail seats with either a 2-part or a single-part UV activated epoxy, and we're now doing it in all new ties before they go out to the field. And it can cut rail seat abrasion. Our tests have shown by as much as 200%, sometimes even more. And it's a hardness between 80 and 95 durometer short D. So it's really trying to limit the ability for water to penetrate that structure to begin with. Another interesting project we've been working on is some half-frame ties with the company SSL. It's a very interesting concept, and what they're really trying to do is increase the bearing surface and try to maximize, again, the fastening system bearing area on the rail. We've got them in a couple different locations, some bridge approaches. We've got them in underneath some IJs, got them in a curvature, a 7-degree curve in Oregon that we're going to use also as comparison to the other ties that are going to go in later this year. So really trying to put them in our key maintenance areas. Again, that's really where our head is at now. Is we've got a lot of success with just regular tangent ties, but it's those key maintenance areas, curves, bridge approaches, IJs that we really want to focus our research efforts on. So some key features again, larger bearing area, larger friction surface, so they provide a lot more lateral restraint than a traditional tie, really prevent a curve from moving around. Use a Oslo fastening system, which is a system that has a lot of advantages. Very tight quality control, quality assurance on these ties. And it utilizes an under tie pad, which is another concept we've been involved in for quite some time, but using it in this application is a little different. and it's trying to really maximize the ballast loading on the bottom of the tie, trying to get as much bearing as we possibly can. So here's some photos of what was there before, and you can see this is a very demanding curve. It's uphill, 7 degrees. It's one of the harshest curves basically on the whole UP. And the existing fastenings, don't get me wrong, I mean, those ties are, I believe, early 90s. So they've lived a long and healthy life, but still, we're starting to see where the insulators have worn in or gone, and we're starting to wear rail into the shoulder. So really wanting to address this issue. So there's a photo, the after photo of these ties. Again, it's a very unique concept. They've been in almost a year now, getting close to a year. So we're going to continue to monitor them. We think it's something that's got a lot of potential. Here they are in the bridge ends on the South Morrill sub, which is one of our heaviest tonnage territories there too. Trying to level out that stiffness going into the bridge, trying to maximize that bearing area, reduce the ballast degradation, everything that goes along with that at a key maintenance area at the bridge end. But going forward, again, we're going to continue to monitor them, and we think they have a real high potential to provide relief in high maintenance areas. You know, I want to say thanks to a few people: Chris Ruzick, John Jerome, Eric Geringer, my old boss Antonio Buena, Gary Click, and Gord Weatherly with Boast Alpine for their help with all this pictures and everything else for this too. So kind of some final takeaways. Dwight talked a little bit about rail industry. It's healthy and growing. It's a very interesting industry right now to be in. You know, you give you a little insight into our infrastructure, what we're up against. Try to talk about how we're trying to capitalize on technology. We're looking for solutions that are practical and cost effective. And we're really using research that's driven by demand, trying to attack those high maintenance areas. For UP, it's a very broad and diverse company, specifically the engineering department. It's a very rewarding work environment. You guys can see I'm a younger guy. I haven't been out of college too long. I never thought for 2 seconds I'd work for the railroad, but it's an extremely interesting place to work. I can't stress to you enough how much opportunity there is right now. If you're willing to get out there, get your hands a little dirty, and get involved. We basically will take all sorts of different engineering degrees: civil, construction, electrical, electronic. It's getting your foot in the door. For us, the easiest way to find additional information about up.jobs. There's a lot of opportunity out there. A lot of older people getting ready to retire that we need to backfill, and it's not that I'm trying to shove them out the door or nothing, but I want to say thank you, Riley, you and your team. This has been an absolutely fantastic few days. I know Dwight and I and Chris have been very impressed with everything you guys have going on here. Again, Dwight said you're head and shoulders above everybody else as far as rail research and even just regular engineering. It's been very impressive. Really enjoyed our time here. And with that, I think we'll open it up to questions. Ready? So the question there was the high-speed turnouts for the Spissel line, if they're capable of handling freight traffic as well. They absolutely are. That's where our struggle is. So that there will be freight traffic on that line as well too, but it's mixed. I think it's intermodal, it's some light manifest trains, so it's nowhere near, say, a coal route. So I wouldn't go put that turnout out on our heavy coal route. So what we're doing is trying to adopt that technology, but do it on some different manners. Try to get that spiral in there, but keep the points thick. We've got some what they're called clothoid geometry, which is a similar concept that are out on our Columbus sub. There's 8 of those that went in last year that we're trying to do a lot of the same things. So the concept could definitely be adopted for that, but that particular turnout, no.
Right. Yes. I don't think we have a level on that yet. I think that it's going to be more and more we can get the track geometry systems technologies on both. Where you might have a VTI, just to give you a scope, with the VTIs right now, there's 52 of those that we get the information from. We do about 2.2 miles a year with that. That's right. So, I mean, that point.
Question from Mike Roney of Canadian Pacific. If you could stand behind the computer, for some reason the microphone works when you stand there. Anyway, Mike would like to know, how do maintenance of way forces respond to low priority vehicle track interaction?
We're not responding to the low priorities. We basically are handling it. We handle if it's a high priority, and a high priority is 24 hours. A medium priority is handled you got to do that within 7 days. So.
And another question, Dave Thurston from Parsons would like to know, what speed do you allow for your number 24?
Right now we've got them at 50, but they are capable of doing 60 and having pretty high passenger comfort. There's some other reasons why we have them at 50, but long term I think we'll be using them at 60.
Well, there's a lot of advantages to be to trying to do that, to put things out there automated. There's some disadvantages because you can't see what's out there. And when a guy physically goes to the track, and that's where maybe as we go forward, the visual systems, as they grow and get smarter, then that might be something that can offset some of those things. But I think that the visual systems will probably be something they'll have to do, but there's always some things that the guys will do, and they have to do inspections. They might have to walk, and they might have to look at some things. So some of that stuff might still go on, but you might be able to get the benefit of having the automated things to help him with this, or direct him where he needs to go look at. So. We do, and whenever every day we get a list. Well, there's several ways this goes, but every day we get a computer screen that comes in the office for everybody that has a run that'll show what the high hits are for the areas, and also if there's an event that they're having to do work that's in their if the maintenance track maintenance guy, like a major track maintenance would be a guy that would be doing that. He comes in the office and he pulls the computer up and says, "Hey, I've got a high hit over here." One of the things they can see is how many times it's hit. So how many repeats that we've had on that same area. And we have a certain criteria for, like, if it's within so many feet of that hit, then it becomes we say that's a repeat area. We have, and there's some things that, some basic things you have out there. If you have, like, maybe you have a flat spot in the rail, for example, it'll take a hit from a vehicle, or actual vehicle is what we call them. If you have we have a place where we call an interlocker, where we cross two railroads. That always has high hits as you go across those, because you're going, you're hitting as you go across the railroad. So, based on the different speeds, you're going to probably see some higher hits and stuff. So those are the things that, that we saw. So there are some things we see. Some of the things we know about we've got the system smart enough that they'll come up and say, hey, this is a railroad crossing. So we know what's going on at that location. Yes. Slab track? No slab track. So yeah, no. We just, freight railroad wise, the slab track, my opinion, slab track is probably not going to work. Because if everything is perfect, you get a little more perfect when you're out there dispatching, you don't have all the loads. But problem is, if you have a slab track environment, you put a wheel down from whatever reason, you burn a journal off, or on a train, or whatever you have happen, something happens, you have a problem with the railroad that puts something down, you're going to tear that railroad gone, and your railroad's gone. And so what are you going to do to get back? And that's a big thing for us. If we have a service interruption out there for us, we've got to go out there and get something in. So we got to have track that we can we'll panel out, we'll slide in, like concrete tie railroad, which is a big issue for us. A lot of times what we do now is we'll push the track out. We build these long super panels that we call them, and we'll slide that in the track. So we actually have 80-foot track panels that we put in track. And then, we'll put those, connect them together while they're, rebuilding track, and slide those into place. So you got to be able to maintain it. And right now, I just don't, in my opinion, I don't really see the freight rails being able to do that. Maybe future, long years down, maybe something that could do that. But it's got to be a perfect railroad to be able to do that.
You're just talking almost constantly. Usually you don't have one without the other. We try to maintain before they become a problem. We've been really aggressive too with just our pad and insulator replacement projects before things ever get to be a problem. But it's sometimes just for us right now. Sometimes the ties just get so worn out over time from having all these issues with the insulators and pads that we just have no choice but to replace ties. But usually you're not seeing one without the other. For us, it's usually when you get into the shoulder, more than, we have all sorts of different requirements, but if you get in 1/4 inch or more, you're pretty much done. We've tried a lot of shoulder repair processes, and we've had some success with them, but sometimes it's too much, and we choose to replace the tie. So for us, we have a tremendous amount of data on those other types of ties, wood ties, composites, and all sorts of curvatures and tonnages, and we have good baselines for those, how long we think it'll take until we start having gauge problems and plate cut and all those other issues that come with that. We're really looking, the second part of that question, I think, is with the concrete ties. We looked at varying the spacing, using some alternative concrete tie designs too, like the SSL ties. We're using some wider footprint ties from some of the other manufacturers. So we think we've got a good baseline for everything else. It's now, what's the baseline with these different concrete options?
Anybody out there on the internet want to ask a question? Mike Garcia would like to know how the owls are doing.
Excellent, excellent. So for those of you who don't know, an owls is a one-way low-speed diamond, which essentially you run on the flange of the wheel or the little tip of the wheel. For one of the routes, you're limited to 10 mile an hour per the FRA requirements. We've had a tremendous amount of success with them. It's not without its trials and failures. We really got to be cognizant of the low angle where you increase that gap that the wheel has to cross. We try to put them in wherever we can. We're looking at some full flange designs too as another type, possibly long term. But we think there's a tremendous amount of opportunity there to reduce impact loads.
Yeah, so you said you're looking at, do you have any of the two-way flange bearing in service?
Not yet, not yet. We're hoping here reasonably shortly. There's a lot of issues with those too that are being worked out that we're hoping to get resolved here soon.
We're good followers on that. We've got owls here, and actually the diamond right near where we have dinner last night is an owl.
Yeah.